A new chapter which is very one of the important chapters in mechanics, that is work power energy, which has even collisions as second part of it. So here before discussing with the actual topic, let us discuss something related to dot product of two vectors. Something related with the dot product of two vectors, let us discuss. Now say suppose for example I have a vector, that is a vector. We know vector is what? Any vector is a physical quantity that has both magnitude and direction, and the arrow indicates its direction. And say I have a b vector, something like this, and theta is the angle from a to b. Theta is the angle from a to b, not from b to a. I have taken theta as angle from a to b. We can take angle from b to a also as theta. Now a dot b, what is a dot b basically? This is multiplication of two vectors. We are multiplying two vectors. We know multiplication of two vectors can be done using dot product or cross product. So here we will be discussing only with the dot product, because work is a scalar and dot product result is also a scalar. Now how is a dot b defined? What is the definition of a dot b? A dot b is defined as magnitude of a, whatever is the magnitude of this vector, into magnitude of b into cos of the angle. If you are taking a dot b, then the angle should be taken from a to b. So from a to b I have taken the angle as theta, so it will be cos theta. This is how a dot product is defined. So you can find out dot product as a magnitude of a into magnitude of b. Simply multiply magnitude of a into magnitude of b into cos of the angle between a and b. Now this can be understood in, this is one way, this is the first way. This is the first way, that is simply take magnitude of a, simply take magnitude of b and multiply with the cos of the angle between the two, that is a dot b. There is another way of understanding a dot b. So a dot b can also be understood as, I can write this as say a into b cos theta. I will separate it out. So this can also be written as a into b cos theta. Now what is b cos theta actually here? So a vector I have kept it as it is. If this is b vector, if I find what is a component of this b vector along a vector, if I find what is a component of b vector along a vector, so I will get basically this component will be b cos theta, the horizontal component, and that is along a or parallel to a, and this is b sin theta, and that is a component which is perpendicular to a vector. So this can also be written as a into b cos theta. A is simple magnitude of a into what is b cos theta. B cos theta is nothing but the component of b along a. What is the component of b along a? Component of b along a, if I resolve b along a, I am getting b cos theta. So I can write this also as magnitude of a into the component of b along a. Simply instead of writing as a magnitude of a into magnitude of b into cos theta, you can also write a dot b as magnitude of a into component of b. B cos theta is nothing but component of b along a. Component of a b vector along a. So this is a dot b. Another way of writing a dot b is, this is the first way, this is the second way of writing, this is the first way of writing. And the third way of writing a dot b is, I can group a into cos theta as one term into b. A cos theta into b. This is not cross product, it is just multiplication, normal multiplication we are discussing. This is also just normal multiplication. Now what is a cos theta? Now again if I draw the diagram here, so this is a vector and this is a b vector and this is theta. Now like how I resolved b cos theta, I told it as a component of b along a vector. Similarly a, if I resolve, I can resolve it into two components, one along b and one perpendicular to b. So a, if I resolve it along b, so this will be how much? This will be a cos theta, one component of a. I have simply resolved a as, this is theta, so this component is a cos theta, and the other component has to be perpendicular to a cos theta. So that will be in this direction, perpendicular to a cos theta, that is a sin theta. So I am not interested in a sin theta, I am just interested in a cos theta, because I want what is a cos theta. So I can tell a dot b as simply b, like how I wrote b multiplied by a cos theta. What is a cos theta? A cos theta is nothing but component of A along B. So A cos theta is nothing but component of A vector along B vector. Along what? Along B vector. So this is the third way of defining A dot B. So all the three definitions are very, very important. A dot B is simply what? Magnitude of A multiplied with magnitude of B into cos of the angle between them. That is first way. Second way is what? Just take one vector, that is A vector, magnitude of A vector into, no need to see what is the angle between them. So B cos theta looks like what? B cos theta is nothing but component of B along A. So I can write A dot B as A vector, that is the magnitude of A vector, multiplied by component of B along A vector. Third case, if I see, I have kept one magnitude as it is, that is the magnitude of B vector. First I kept a magnitude of A as it is, now I am keeping magnitude of B as it is, multiplied by A cos theta. Now what is A cos theta? A cos theta is nothing but component of A along B vector. So simply I can state that multiply those two components that are in the same direction. So here if you see A cos theta and B are in the same direction, multiply that will be the dot product. Here which are in the same direction? B cos theta and A vector are in the same direction, so multiply their magnitude, you will get basically what? You will get basically A dot B. So A dot B can be written as either magnitude of A, magnitude of B into cos theta, or another way of writing is take one magnitude as it is. Either magnitude of A you take it as it is, or you take magnitude of B as it is, multiplied by component of the other vector. Now if I have taken A vector magnitude as it is, I have to take component of B vector magnitude, basically it's a magnitude, component of B vector along A vector. In the second case, if I am writing B vector as it is, here in this case if I am writing B as it is, magnitude of B, I need to take component of A vector along B vector. That is the definition of A dot B, and it is understood that it is the magnitude, because dot product is always a scalar quantity. Now let us see, this is the meaning of A dot B. Let us find out what is B dot A. Now what is B dot A? B dot A is nothing but like how I define A into B into cos theta, like that it will be magnitude of B into magnitude of A into cos of angle. A dot B was angle from A to B, angle from A to B. Angle from A to B was, I have taken it as plus theta. So here I have to take cos of the angle from B to A. So from A to B if I take it as theta, then the angle from B to A will be minus theta. This is clockwise, I have taken positive, so this will be anti-clockwise, negative. So cos of minus theta, so it will be B into A into cos theta. So if I compare this and this, both are actually the same. Instead of writing AB, I have written BA. It's like x into y same as y into x. So both are same. So this implies A dot B is equal to B dot A. So therefore we can tell dot product is commutative. So it is, I can generalize and tell that dot product is commutative. This is one property of a dot product. Dot product is a commutative. Next thing, now dot product is also called as a scalar product. Dot product, it is also called as a scalar product. It is also called as a scalar product. Now why it is called as a scalar product is, though what the two entities what we are multiplying are vectors, this is also a vector and this is also a vector, the final result what we get is just a magnitude. Magnitude of A, magnitude of B into cos theta. All the three are magnitude. So if you basically all three are numbers, if you multiply all three numbers, we'll just get one number, and that is a scalar. So that's why we tell it is a scalar product. Though these two entities what you are multiplying are vectors, the final result is a scalar. So that's why it is called as a scalar product also. So dot product is a scalar quantity. The result of dot product is scalar. So this is the second point. Now example is what? I can give many examples. Let us discuss the examples, commonly used examples. Work done. Now if I tell work done is a scalar. This is scalar. Work done is scalar. Work done is basically what? Force multiplied by displacement. So force into displacement. Displacement I'll denote it by say yes. We know force is also a vector and displacement is also a vector quantity. So here I'm actually multiplying two vectors and the final result is scalar. So when can it be? I have two entities which are vectors, and final result if I'm getting scalar, then the operation, then the multiplication should be dot. So if I write in the vector form, it will be F into S and the operation is a dot. So work done is nothing but a scalar product of force and displacement. So this is one result. Now second thing, potential energy. Potential energy also can be written. So du, this we will discuss later. Du is nothing but the dot product of F into dr vector. Integral du will be equal to integral F dot dr. So this is one way. This we'll understand what is it in the coming classes, in the coming sections. Now kinetic energy. Kinetic energy, we know kinetic energy is half into m into v square. But we know that velocity is a vector and kinetic energy is a scalar. Energy, work done, potential energy, all are scalars. Therefore, this equation is actually written as half into m into this v square is actually written as a v dot v. So that the result of v dot v is a scalar, mass is a scalar and half is scalar. So the final answer also will be scalar. So actually that v square is written as v dot v. Why v dot v? Because v dot v will be what if I write here? Magnitude of v into magnitude of v into cos of the angle from between v to v. Since both are same, the angle is 0, cos 0 will be 1. So v into v is v square. So v square can be simply written as v dot v, and this is a scalar result and this is a scalar quantity, but individual vector velocity is vector. But if I take the dot product of the two, it will become scalar. That's why kinetic energy is also a scalar quantity. These are the examples, some of the examples.